The terms time of flight and mass per charge are very important terms to understand when you're working in mass spectroscopy. And they're very important because they are what get us these plots at the end of the day that allow us to determine information about what we're studying. And so in this video, what I'm going to do is talk about how we are evaluating these times of flight as well as the mass per charge in practice. And so the first thing we're going to do is go back to physics, E&M, and recall what the definition of voltage is. Voltage, V, or delta V, a potential difference, tells us the amount of energy per charge, joules per coulomb of charge. And what we can rewrite that as is this. So joules will have some units of potential energy, and coulombs I'll call Q for charge. And so if we examined some ion that we just created with our laser in MALDI earlier, when it is at the plate side on the opposite end from the detector, there's going to be a potential energy difference between these two sides, PE. And so we can evaluate PE quite readily by solving for PE is equal to Q times your voltage, which I'll call V, or delta V. And so when all of this potential energy is converted into kinetic energy at the other side when it slams into the detector, the kinetic energy of this fragment can be described simply using 1/2 mv squared. And so all of the potential energy goes into becoming kinetic energy. And so what we can do is we're going to equate the two. I'm going to let QV be equal to 1/2 mv squared, where little v is the velocity. And in this case, because we're dealing in mass spectroscopy where multiple charges can exist on a molecule, depending on how many or how effective the laser was at any given instant in time, I'm going to let Q be equal to Z, which will represent the number of electrons or protons that are added or removed. And then we're going to multiply this by E, which is the charge per electron. And E is constant 1.6 times 10 to the minus 19th coulombs. And this is a physical constant. We're never going to change that, but I will substitute in Q is equal to ZE in this relationship here. And so when we do that, we now have Z charges times the charge per electron or proton removed times the voltage must be equal to 1/2 mv squared, where m is the mass of the fragment, and that includes the protons that are on that fragment as it's traveling through our mass spectrometer. And so what we're going to do next, because we are interested in time of flight, I'll call it TOF, we'll recall the definition of velocity, which is equal to some length over time, in this case time of flight. And in this case, length is the length of our vacuum chamber in our mass spectrometer. So we know that that's defined, and we will solve this equation for velocity. And so when we do that, we'll get velocity is equal to, we're going to have 2 times Z times E times V, quantity divided by the mass, and we're going to take the square root of this, and this is equal to L over time of flight. We can now evaluate time of flight quite simply as the following. So we just multiply both sides by TOF. We'll have the length of our vacuum chamber times, and then 2ZeV over m raised to the minus 1/2 power. And so we've just defined what the time of flight is in our system, and we're a step closer to determining what our mass per charge is. We'll realize we have the inverse of mass per charge right here in our equation, And so performing a little bit more algebra, we can very easily find that the mass per charge, it will be the following. So we're going to have m over z is equal to, we're going to rearrange this equation here and solve for m over z, and to find that it is equal to 2 times the charge times the voltage times velocity raised to the minus second power, and this is equal to 2 times e times v times the inverse of velocity, which would be time of flight, divided by length of our vacuum chamber, quantity squared. And we have just evaluated what the mass per charge is in our mass spectrometer, so we can generate plots like we see here. And so this concludes how we're able to get these important quantities to begin to examine these kinds of mass spectroscopy spectra. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.